Today, I want to talk about this problem 3505, minimum operations to make elements within K subarrays equal. It's a hard problem and it kind of requires the idea from another hard problem. If a lot of people would have heard of it, called the sliding window median. So we'll come back to that later. Let's try to understand the problem statement. So you're given an integer array nums and two integers x and k. You can perform the following operation any number of times, including zero. Increase or decrease any element of nums by one. So basically, you can pick any element and then change it to some value, uh, either incrementing it by one or decrementing it by one. And each of that increment or decrement will be considered one operation. So you're supposed to return the minimum number of operations needed to have at least k non-overlapping subarrays of size exactly x in nums, where all elements within each subarray are equal. Okay, so let's see a sample case first. So given this input, this nums array, x equal to 3, k equal to 2. So you're supposed to have two subarrays in this array, two subarrays of length x, of length 3, which have the same value. So suppose this array and this subarray might have the value 3 and this subarray might have value -1. So then it'll be considered the values of all the elements should be equal. And you're supposed to have k such subarrays and you need to find the minimum number of operations to make that happen. So in the sample case, let's see. Use three operations to add 3 to nums 1. So you're adding 3 to this, making it 1, which will require three operations, right? -2 plus 1 is -1, -1 plus 1, 0, 0 plus 1, 1. So three operations here. And use two operations to subtract 2 from nums 3. So at this place, you subtract 2 and make it 1 again. So you'll have these three values equal to 1. And you took 3 plus 2, 5 operations here. In the next, for the next subarray, you use one operation to add 1 to nums 5, right? So here you add 1 to make it 4, and two operations to subtract 2 from nums 6. So you make this 4. So you'll have 4, 4, 4, which is length 3, and you have two arrays like this. So this array with values 1, this array with values 4, value 4, right? So in the end, you just add all the operations. And in this case, the answer was 8, right? So this is the problem statement. Now let's try to deconstruct this. So this is your subarray, right? Now x, given x was 3 and k equal to 2. So in this case, what they did was make all the values in this subarray as 1 and this subarray as 4. And they said that the operations needed to do this would be the minimum, and it came out to 8. Now, problem 1. Given a sorted array, suppose 1, 3, 5, 7, and you can decrement or increment any number by 1, and you need to make all these elements equal. So this is the first idea behind, okay, let's just call it idea 1. This is the first idea behind this question. So uh, the minimum number of operations will be required when you try to convert all the elements to median of this. So think of it in a number line. You have two elements, so 1 and 7, right? 1, 7, and 10. So If you try to convert everything to 10 in this case, this would be three operations required, this would be nine, right? Giving you a total of 12. But if you convert 1 to 7, this is 6 and this is 3, giving you a total of 9 compared to 12, right? So, why this works is when you're trying to make everything equal, you want to converge everything to the center of it, right? Because if you take two elements or three elements, the best way to do this would be to converge 1 to 3 and 5 to 3 towards the center. And mostly the operations will be minimized when we're trying to convert the number into median. So this is the idea that you're supposed to get seeing this question. Okay, so this is a hard question consisting of two hard concepts. So one of them is DP. So just knowing DP will make the question work with smaller constraints. But why I'm talking about this median right now is you need DP plus sliding window median to make this work. Because if you try, okay, we'll come back to this DP solution later. So we just talk about the idea right now. Okay. So um, this is the first idea. So whenever you're trying to minimize all the elements to some value, the best way, the most optimal way would be to convert them into the median, right? So we now know we need to find the median given a bunch of elements. Suppose x equal to 4 in another input, x equal to 4. You need to find the median in this subarray of length x equal to 4 and then try to converge all of the values towards the median value. So basically, what you ideally want is a sorted array. So this 7, 9, 13, 15, you would convert it into everything to 13. But in this case, the array is not sorted, right? Or the subarray of length x equal to 3 is not sorted. So these are all unsorted elements, right? So you need some way to calculate the median of each subarray of length x without taking too much time. So if you do it in a brute force way, um, what would you do? You would you would sort this. So we have a subarray, you would sort this in x log x and then go through the entire array for all subarrays of length x. So this would be nx log x, which is not feasible. I'll go back to the constraints in some time, but take my word for it right now. This is not a feasible solution. So you need to know something called an idea called the sliding window median. Now, uh, what do we do in this? How do you calculate given bunch of numbers 13, 7, 8, 9, 1, 3, 2, 7. And you're supposed to calculate the median. All of this is unsorted. You're supposed to calculate the median value in a subarray of length in a window of size 3. So you would calculate the median of this window, then include the next element, then include this, and so on and so forth, right? And you need to do it in a way which is feasible. So you can't be sorting it, storing everything in a temporary array and then sorting it and then finding the mid value. That would require, as I said, often log x log x, right? So we need to do something which will give us the median of each subarray in better time complexity, right? So idea here is to use two priority queues. So this can act as a refresher for the sliding window median question as well. So you have two priority queues. One of them is a max heap. One of them is a min heap. right? A max priority queue and a min priority queue. This is for smaller number. This is for larger number. Now, what do I mean by that? So consider this subarray. So you have 13, 7, 8. I'll show you what it should look like. What the After you have processed these elements, what the window should, the max heap and min heap should look like after you process the first three elements. So it would look something like 7, 8, and 13. Right? Never mind where the pointers are going. I'm just putting it for the sake of seeing it, what all elements are there in the min heap. So now you know all the smaller numbers, right? So you have a bunch of numbers A, B, C. So among this, the smaller numbers should go to the max heap, and all the larger numbers should go to min heap. What this would do is it will give you a very easy way to calculate the median. So in case the number of elements being processed is odd, you can just take actually at all points, what you're doing is trying to maintain equal sizes. So if number is odd, if the window is of, in this case, in this case, x equal to 3, so you can keep one element extra on the larger heap, or which is a min heap. So you keep two elements here and one element on the max heap, which is for smaller numbers. But every number in this heap is greater than or equal to every number in the max heap. So this is one condition you have to maintain, and the other one being uh, the queue should be balanced. So uh, number of elements in larger, which is this, should be uh, equal to number of elements in smaller in case the window is odd, is even, sorry, and number of L's in smaller plus 1 if it is odd. So you're allowed to keep one more element on the min heap. And every time you want to calculate the median, it's just the top element of the min heap, of the larger heap. So now how would this work? Let's do a dry run of this x equal to 3. Okay. So at the starting, you had 7 this heap, 8 and 13 in this, right? Now you know the median of 0 is basically 8, the top element of that. When I move my window one element to the right, now I have to add 9. Okay. So I have to add 9. So add is 9 and remove is 13, right? So we need to check some conditions. So in this case, add is 9. So you need to add it to the queue uh, by comparing it to the topmost element in both the queues. So 9 is greater than 8. So we know for a fact 9 will get added here, right? And removing 13, you're removing 13. So again, if this removed element is greater than the top of the larger heap, you remove it from that queue. If it's equal to or smaller than the top of the smaller heap, then you remove it from this left heap. So we know in this case 13 is greater than 8, so you remove it from here. And we need to check if the queues are balanced. So as I said, right one, the min heap can have one more element than the min heap or the max heap. I'll just call it left and right to avoid confusion. Yeah, so right can have one more element than left, which in this case is satisfied. So now we again know the median is top of right? So 8 again, which makes sense. So 7, 8, 9 is in, and these are the elements. It's like in sorted, the median is 8. And in first case, it was 13, 7, 8. If you uh, sort it, it'll be 7, 8, 13. The median was 8. Okay. So this is our condition now. Now you again move it one step to the right. Now what you're doing? You're adding 1 and removing 7. So you're adding 1. 1 will go to this side, to left heap, because it's smaller than the top of left. And you remove 1, remove 7. Right? So you remove 7. So now your heap is this. Again, median of 2 of the subarray of length x of x, where x equal to 3 is starting at index 2 is 3, which, sorry, 8 again, which makes sense. So you have three elements, 1, 9, 8. In sorted order, there'll be 1, 8, 9. So the middle element, median is 8. So far, so good. Now we move to, we remove 8. So we add what, 3, remove 8. So where does 3 get added, first of all? So as I said, any element greater than the top of right will get added to right. Otherwise, in the left. So you have 1, 3, 8, 9. And you remove 8. So you remove this. But now our balance condition is not satisfied in this case because we can have one element more in uh, left, right? Sorry, in right. So this will, when we heapify it, it'll be 3 and 1. Okay, so in this case, what we do is we just take the topmost element from left when this balance condition gets uh, violated. We just take the top of one of the heap and give it to the other. Okay, so in this case, we'll take 3 and add it to the right heap. So 3 and 9. So if you have to remember, this is a min heap, this is always a max heap. So now in this case, median of 3 will be 3, right? So this is how we continue. So you just need to remember a few of the cases. So you can dry run this on your own, including the next elements. But the idea here is at every step you need to balance both the heaps. So in my case, num right is equal to num left or num left plus 1 if the elements in that window are odd. So this is one condition. Right is a max heap, left is a min heap, right? Now suppose you have some heap left and some heap right. When you added something to, initially they were both balanced, so both of them had 3 elements in each of them. But suppose you added something which got added to the right heap and remove something which got removed from the left heap. So this messes up the balance of the trees. So in this case, what you do is you just take one element. So now this was 2, this was 4. So this is more than one, right? So in this case, what you do, you take the top of this, which is the smallest element among all these elements because this is a min heap, and you add it to the left heap. So this gets moved, you pull on the right heap and put it on the left heap. So this is how you would calculate median in one pass, moving from left to right. Now, again, there's a catch here. So this remove part, So suppose if you were only removing from the top, which is dot poll in Java, right? In that case, that's an O of one operation, right? And to heapify both the heaps will be O of log k, k being the window size or log x, right? And you're going from 0 to n minus x size of window, right? So which would give you a time complexity of log x, majority element being n, so n log x. But this is only in the case where you poll from the top. But if you notice in our this dry run, sometimes we were taking elements from the bottom of the queue. So there, this suppose you have a queue called PQ, and you remove some element in Java dot remove, right? Nums I. And suppose this nums I was taken from bottom of the queue. So this was nums I. So this is not an O of one operation any longer. This is of time complexity k, or let's say x. X is the window size, right? So in that case, our whole solution becomes x log x, nx log x, which is not decent enough for the question we're trying right now. So there's a trick here, so, which is called the lazy removal in a heap. So what this lazy removal is doing is when this operation of remove is coming, we're not actually removing it from the priority queue. We're just marking it as we have found an element which is not supposed to be there. So given two heaps, this was a right heap, this was a left, this was a max heap, this was a min heap, right? Or this is for the larger numbers, this is for the smaller numbers. Easy. So you just add it, and that's an O of log k operation, right? Now, if we just use some function called dot remove in Java, that'll become O of k, right? But we don't want that. We want the maximum factor to be of log k, not k, right? So suppose some add came and we added it to this side. This was the new node. And the remove was from left. We removed it. Originally, without this lazy removal, we would call L dot remove this number, right? But in our case, we're not doing that. We are letting that element, this element, to be there, but we're marking it in a map. We're saying map of, let's say, y is 1. So let's just call it L map. This was a left map. And if something is removed from the right one, we call it um, R map, and we keep a count of how many times it has been removed. So whenever some value has to be removed from one of those heaps, we do not actually call dot remove. We just mark it in L map or associated map of the heaps, and we increase the count. So if it was at 0, we just increase it to 1. So suppose if there was another stale value, let's call it stale value in this part, which was M, we would say L map is M and 1. And if you see another stale value with Y, you increase this to 2. So idea of lazy removal is we do not touch the value which is to be removed unless it comes to the top of the queue. So if after some operations you see there is a lazy value here, only then you'll pop it off. Otherwise, you do not touch it, you let it be on the queue. And you just mark it that we have found a node which is stale with this value and it exists on this left heap, so associated with the L map, right? And after certain operations, when it comes to the top, I'll talk about it, you just pop it off. Okay. So this messes up one of the conditions of our median calculation. We said our heaps are supposed to be balanced, right? But if in letting the stale values be present in our heap size might uh, violate the balance condition. So you're adding something, but stale values stay in. So stale values stay in. This heap size will grow, right? And the balance will mess up. So you cannot calculate the balance now in terms of sizes of the queue. So you cannot say r dot size uh, check balance. You can't say if r dot size equal to l dot size if it's like the window is even in length. So you need another variable to keep track of this. We'll just call it balance. So what balance is going to do? So when you have two queues, when you add something to the queue, to the right queue, I would decrease my balance value by one, right? If I add anything to the left heap, I would increase my balance value by one. So any element addition on the left increases the balance. Any addition on the right decreases the balance. So my balance condition is basically my balance has to be 0 or minus 1 because I need one more element on the right tree, right queue, right? So this is my new balance condition now, not in terms of sizes of the queue, but in terms of a variable which will be incremented or decremented whenever we add or remove to either of the heaps or the queues. So now, if you remove from this, that's technically incrementing balance by one, right? If you add to the add to the right heap, it'll decrement the balance by one. If you add to the left heap, it'll increment the balance by one. But if you remove from right heap, it'll increment the balance by one. So let me just put it in an arrow. So if you're removing from right, balance increases. If you're removing from left, balance decreases. So, as I said, whenever you have to remove a value, you just mark it and put it in a map. At the same time, what you do is you decrease. So, if you're removing from the left heap, you decrease the balance by one. If you're adding, you increase the balance by one. Similarly, if something is being added to the right heap, you decrease the balance by one. If it's being removed from right heap, you increase the balance by one. So this is how we'll now take care of our remove. Instead of removing it using something like dot remove in Java, we would just mark it in a map and then decrease or increase the balance. So technically, you can think of balance representing a heap size, right? And a new balance condition is either it's a 0 or minus 1. Okay, so this is something called lazy removal in a heap. Uh, and we need this in this question, right? Now coming back to the question. Okay, so now we know how to calculate the median values. Okay, and sorry about this. One more important thing. You also need to calculate the cost while you're doing it. What would the cost be? What will the cost look like in such a case? So we are not just finding the median for the sake of finding median in this question. Sorry. We need to find the cost associated by with the converting all the elements in that window to the median value. So how you would do that? So we know this is the median, if this is the median, then to convert everything in the left, right? So you would, this is the left, what is the sum of all these values? So suppose you have 3, 2, 1, 7, 8, 9. You're supposed to convert everything to 7, right? So the idea here is we'd also have a left sum and a right sum, representing the sum of values in each heap when you're calculating the median at that point, right? So left sum in this case would be 6, 3 plus 2 plus 1, and right sum would be 15 plus 9, 24, right? So to make all of these into median, which is 7 in this case, what would uh, the equation look like? It'd be 7 with the median into the size of this heap, let's say x by 2, right? Our window size was 6, suppose. So number of elements in this is 3 minus left sum, right? To calculate everything in this to the median, which would be 7 into 321 minus left sum is 6. So what's that? That doesn't make sense, does it? 1 to 7, so 7, 7, 21. It does make sense. 6, 2 to 7, 5, 3 to 7, 4. So, okay, yeah, 15, it does make sense. So you'd require everything in the left heap uh, to convert to 7 using this formula. In same way, for the right tree, you need median into x by 2, right sum, which obviously will be greater because it'll be or everything is greater than the median because this is a min heap, right? The smallest element is on the top. So this will be the formula for this side. Convert every node in this to median, and then you would just do summation on them. So this way you would have for each window the median and its cost. So we don't care about the median once we have the cost. So we are only calculating the median to calculate the cost. So in each window, we now know the cost associated. We first know the median by our sliding window and lazy removal, and we know the cost. We're also keeping track of left sum and right sum. So on top of the values themselves, we are calculating the sums as well on each side of the tree. So left sum and right sum. So you know the median value now, and you know the cost. So you know the cost of this subarray of length x, C1. You know of this C2. You know of this C3 and C4. So now we have the cost associated for that subarray of size x to convert it into median for every index, like subarray starting from each index. So this is the basic we need to actually solve the problem now. Now let's go back to the problem. Okay, so now coming to the DP, what is the recursive solution? So this is a very classic problem of take and not take. So you either take something. In this case, what take tells you is, do you start the subarray from current index? Not take is don't. So take is you start, not do you. You start the subarray from current index, and not take is don't start it. Like skip it and go to the next one. So I'll first just write the recursive solution to this. It'll be very easy to follow through. So I need the current position first of all. I need k. So in the beginning, you would return solve of nums starting from position 0, and you need k subarrays, right? So we are passing that value as well, and x. So in this, let's write the recursive case first. So long of case 1 is I skip it. I do not, this is the not take case. So I'm not starting my subarray, one of the k subarrays from this index. I'm just incrementing the position. So I choose not to take in this case. So let's just say it's now we need the minimum operation. So, and also we need to check, make sure pos plus x. So whatever current position you're in plus x. So you need a subarray of size x, right? So that shouldn't exceed n, right? Now, let's imagine we have calculated that cost array that we were talking about. So that whole cost array was, and if you start the subarray from here of size x, this is the total cost. We'll come back to it. That that was the cost. So this is why we needed something quick. Otherwise, we'd have to run a, suppose we had the median and not the cost, right? Median array, sliding window median. So in that case, I would go through all the elements in this x size window and calculate the operations needed. But we don't need to do that, assuming we have this cost array, right? I'll come back to this. So in this case, case 2 is the case of starting the subarray from this position. So this is solve of nums. Okay, one more thing, you can just skip everything in between. So once you started the array, you can move x places forward because you are considering this to be the start of the subarray of length x. So you don't need to see anything in between. And because you change this, right, using ops cost, you can decrease the k value by 1. So for the next iteration or for the next positions, you only require k minus 1 more arrays, right? Yeah, so this is my take case. And my result is just math min of case 1 and case 2. So take and not take case and return rest. Now for the base case. So if you have reduced everything to 0, so you have found k subarrays, then you can just return 0. If not, and you have reached the ending of this array, if you reach the ending of this array, you return, and k was not 0. So you haven't found k subarrays of length x where all the values are equal to 0. In this case, you return max value. And just to, if case 2 is not returned as long dot max value, you add ops to it, right? So you start, this is the number of ops to convert subarray of length x, starting at that position. So this is my complete DP solution to this problem, right? But again, this is a recursive, so this is exponential. So we need to memorize it, which we'll come back to later. And if we do like cache the results, this is of n, this is k, k can be 15. So this will be of time complexity. Just this DP solution would be what? It'll be n into k, which is acceptable, almost linear because k is 15. Now the problem becomes finding the median array, right? Or the cost of each one of them, right? So I'll just quickly uh, go through the solution. So let's say it's fill cost. You pass nums and you pass x, right? You have an array of size n, okay, and a priority queue. Integer the smaller heap, or let's just call it max, which is the left queue. And this was the max heap, right? This was the max heap. So in Java, you would do collection dot reverse order, and you have another queue. I'll call it min, which is a min heap. So that's the default priority queue in Java. So for the first case, for the first window of the sliding window, we know X. We need all of costs associated with all subarrays of length X. So first solution for the first window is very simple. So what you do is for X times, just add everything in the bigger queue. So the min heap, which is for larger elements. And we also have a right sum. Let's keep it out of it. Left and into 0 and right equal to 0. So you're adding to the right side, right? So I would have nums there. So first step, I added everything to the min heap, which is for larger elements. Now for x by 2 times, I would remove from the min heap, right heap, and put it to left heap. And you know only this, so because right queue is the right priority queue is the min heap, the smallest elements will be popped and moved to the left tree. So you would have all the smaller ones on the left and all the bigger ones on the right. So min dot poll and then add poll. Now because I removed from the right queue, I, I subtract it and I add it to the left queue. So I add left sum. So at each time, we'll have max size equal to x by 2. So for the lower heap, for the min heap for lower elements, which is called max in our case, is x by 2. And min size will be if x is divisible, divisible by 2, then will be x by 2. Otherwise, it will be x by 2 plus 1, right? And now we know the median, right? We know the median to be peak of the min for the larger element, right? So we know for a fact cost 0. Let's say we have a cost array is max size into median, uh, which is what? Min dot peak, right? Minus left plus right minus min size into min dot peak. And at this is just the starting window. So you haven't added and removed till now. You just have added. And in this case, what can we say about balance? So again, balance, if the window size is divisible by 2, then you would have what? Balance equal to 0. So equal number of elements go into left, which would increment the balance by 1, equal on the right, which would decrement. So you would end up with 0. Otherwise, it's minus 1. So one more goes in the right one, which is equivalent to decrementing. Now, mm, you start your next window. I plus x minus 1 is less than n and I plus plus. So you have in as nums I plus x minus 1. So this is the new one. And out as nums of I minus 1, right? Yeah. Okay, I think this video is getting too long, so maybe I can just go through instead of writing the code. I can just go through like already submitted code, I guess. Yeah, so okay, in this again, so for the first window, I just calculate in of whatever is coming in and whatever is going out, and then check the conditions. So the new element coming in, if it is greater than min for max, so basically right heap, if it's greater than the right priority queue, that means it should go to the right. So you add it to the right queue, you add into the sum, and you decrement the balance. Otherwise, you add it to left, increment left sum, and increment the balance. Now for remove. So this is a like a special case for a lazy removal. So here you're not calling max dot max for min dot remove. You're just marking it in its associated map, and you're decrementing the balance because you're decrementing from the left heap, which would decrement the balance, and then decrementing the left sum. Otherwise, you remove it from the right heap, and you increase the balance, and you decrease the right sum. Okay. So after this, I'm doing a balance heap operation. So this is to make sure our balances stay equal. So, for example, suppose a new element taken out, so left heap and right heap were equal, and the element added was to the left heap but removed from the right heap. So this would make our balance positive 2, right? But we said our balance should be either 0 or -1, not anything more than that. So this balance heap operation is for just that. So you're checking, okay, never mind this, never mind this. So if your balance is greater than 0, that would mean there are more elements on the left heap than there are on the right heap. So I pull from the left heap, right, and give it to the right heap. So in this, what this operation would do, it decrease the balance by 2 because you removed it from left heap, that is balance -1, and then add it to the right heap, that is again balance -1. So you add it to the right heap, and you decrease the left sum by pold, right sum incremented by pold. Else if balance is less than -1. So this is an example of if the element got added to the uh, right and removed from the left. First they were equal, so balance was 0. So added to the right makes it -1. Remove from the left makes it -2. So this is the case where you have to pull from the right heap and add it to the left heap. And you take care of left and right sums as well and the balance. In the end, this prune heap operation, what it's doing, it's just checking if the top of the heap contains one of those elements which were stale, so which were marked to be removed. So while that is true, I'm just checking if my map contains the top element, if this was a marked element, and I'm polling it and decrementing its value by 1. So this is the entire solution for this 3505. And the easier part was is just like caching it. So I'm just checking if dp-pos-k is not null. If it is not, I'm returning the dp-pos-k. So yeah, thank you. Hope it's clear.